Enhancing SDC verification in SoCs, heatmap visualization, and machine learning approaches for optimal coverage closure. This paper addresses challenges in SDC verification for SoC designed by proposing a novel approach that integrates heatmap visualization and machine learning. We introduce a method to identify the verification gaps through the heat maps and optimize the regression test suite using machine learning, significantly reducing the redundancy and enhancing efficiency by applying this approach. And we achieved 63% reduction in regression testing time and improved SDC coverage, and to 100% for timing exception passes in regression suite. This method advances verification completeness and efficiency, presenting a robust solution for SoC design and verification processes within a constrained development timeline. 1. Chapter 1 is introduction. The synopsis design constraint SDC define critical design constraints such as operating conditions, timing constraint, and timing exceptions, which serve as essential references to ensure the power and performance and area PPA target of the design. Mismatches between the SDC and the actual design intent can result in a potential performance degradation or device malfunction. This mandates the need for a thorough SDC verification. Traditional SDC verification relies on gate level simulation (GLS), and which typically start later in the development timeline and is highly time-consuming. Consequently, this often leads to a significant timing issues being discovered only in silicon, sometimes necessitating the costly spins. Therefore, performing SDC verification thoroughly and confidently is crucial for a successful chip development. This paper represents a novel approaches to address SDC verification challenges by employing the dynamic SDC-aware verification in RTL, and thereby enhancing efficiency. It also poses the use of custom heatmap visualization to enhance the SDC verification effectiveness and employ machine learning ML to optimize the test suite for coverage closure, offering a sophisticated methodology for SoC verification, and Section 2 describes existing approach to SDC verification, including GLS and RTL-based SDC-aware simulation methodologies. Section 3 describes the proposed approaches to enhance SDC-aware simulation and to shorten the verification time using ML-based coverage closure. Section 4 is explain the experimental result and the achievement of this study, and Section 5 provides a summary of the conclusion and future work. Chapter 2 is existing approaches. The gate-level simulation (GLS) is a widely adopted method that operates on a gate-level analysis generated after the physical implementation phase. It's conducted in an environment where the timing information is integrated through the annotation of the standard delay format (SDF) and the output of the static timing analysis, and where designers wanted to ensure that the synthesized analysis accurately represented in the intended RTL behavior. Therefore, performing the SDC verification using GLS often results in a delayed start, as it typically commences post-physical design. Additionally, GLS consumed significantly more time compared to RTL simulation due to its lower level abstraction and intensive computational demands. This not only limits the number of tests that can be executed within the development cycle, but also makes it challenging to complete even the limited test. So the extended times complicates the early identification of the timing issues, increasing the risk of the costly spins and the specific time issues that historically led to early spin include setup and hold violation were only detected during the silicon testing and resulting in significant delays in product launches. In response to these challenges in GLS and the EDA, the electronic design automation tools have introduced dynamic SDC-aware verification as a more efficient approach for early RTL simulation. Figure 1 illustrates how the RTL level SDC verification can advance the start time compared to GLS, allowing issues to be identified earlier in the design process. In this approach, tested vectors developed during a functional verification at RTL level are reused for SDC verification, facilitating comprehensive SDC validation through the metric-driven verification (MDV) methodology based on regression testing. The coverage metric throughout the MDV cycles are illustrated in Figure 2 by enabling the earlier detection of the potential issues. Dynamic SDC-aware RTL simulation improved the verification timeline and reduced the workload associated with the late-stage correction. SDC-aware verification at the RTL level also includes the capability to verify the timing exceptions such as multi-cycle paths, MCP, and force paths, FPs, which are traditionally challenging to address the GLS. For instance, the suspicious simulator used in the study enables the setup violation checks on the MCP and the FP specified the SDC during the design elaboration phase, using the predefined compile option. When a violation detected, the simulator generated error messages allowing the designers to identify the address timing exception early in the RTL development process. This capability enhances SDC verification by streamlining the process and reducing potential delays in later design stages. Figure 1 is a comparison of verification start time reduction between RTL and GLS. The Figure 2 is a coverage metric across the metric-driven verification MDV cycle. However, despite these advancements, the dynamic SDC-aware RTL simulation still faces challenges in achieving a comprehensive verification. The intended X optimism and RTL simulations where the initialization state X values can lead to false positive during the time verification remains a notable issue. To address this, the X propagation feature can be activated. This feature simulated conditions similar to the gate level simulation, GLS, and allows for early detection of potential timing and data integrity issues. When X propagation is enabled, the simulation environment adopts GLS-like X pessimism, propagating injected X values through the design when a setup violation occurs. This setup automatically assesses the stability of the detected violation through the pass or fail outcomes, helping us prioritize critical issues. Failed tests to indicate serious timing issues likely to occur in GLS, promoting the immediate design adjustment or SDC revisions to prevent costly late-stage respins. Conversely, messages from a passing test are often considered false alarm and waived, and providing essential information for error investigation through the schematic tracing and architecture reviews. Using this method, we were able to identify the key errors, which will be discussed in detail in Section 4, covering the experiment resulting in achievement. However, challenges remain in effectively identifying SDC coverage gaps and optimizing regression testing and reduce redundancy and increase efficiency. So to address these issues, this paper proposed two primary solutions: heatmap visualization and to target and address SDC coverage gaps, and machine learning-based optimization to improve the regression testing efficiency by selecting the most relevant test cases and minimizing redundancy, as detailed in the following section. Chapter 3 is the proposed approaches. To resolve the remaining challenges in SDC verification, this paper proposes two key strategies. First, the heatmap visualization method is introduced to effectively identify and address gaps in SDC coverage. By generating heatmaps, we can pinpoint incomplete verification in areas, enabling targeted verification actions. Second, we leverage machine learning techniques to optimize regression testing, and which enhances test efficiency by selecting the most relevant test cases, minimizing redundancy. These two approaches accelerate the verification process while ensuring comprehensive coverage. The following sections will elaborate on these methodologies and their impact on verification performance. A. Efficient gap identification in SDC verification using heatmap visualization. SDC-aware simulation logs and coverage tools typically provide only summarized numerical information such as a source and a destination point. This limited information makes it challenging to perform sequential debugging across all required verification paths that ultimately hinders timed verification compilation. By implementing heatmap visualization, we can pinpoint areas where the verification is complete, allowing us to take targeted action to address these gaps and reduce the risk of the undetected timing exceptions and performance degradation in the design. As shown in the landmass flowchart in Figure 3, the process begins with extracting data from simulation logs, which includes information on whether the target paths specified in the SDC have adequately covered by the test Based on this extracted data, we generate a SDC coverage summary table and heatmap the target design. The heatmap is structured as a cross table, where the rows represent a source point and the columns represent the destination point. With each cell indicating the test IDs and cover a particular path, a single test may cover one or multiple source and destination paths, or in some cases, none at all. So this mapping allows us to visually verify the SDC coverage achieved by the regression test, showing both the number of activated paths and the overall coverage level across the design. On the right side of the Figure 3, heatmap example illustrated the paths covered by each executed test. The top selection of the heatmap provides a summary of the overall test rate, coverage progress, and the delta information from a previous regression test. By tracking the coverage, regression, and test changes, and designers can effectively monitor verification improvement or regression and identify areas needing additional testing. Figure 3 is a workflow with heatmap generation with the example output. During the SDC coverage closure process, each cell in the heatmap is assigned a unique color. The initial heatmap is filled with gray and red, including whether a path has been covered or not. Red cells are changed to a green or blue based on the review of the result. As shown in Figure 4, when the coverage closure is complete, only gray and green cells remain in the heatmap. Figure 4 is a usage of heatmap for coverage closure. And so, in addition, data visualization at a heatmap plays as an instrumental role in a data preparation stage, which is essential for generating dataset, a prerequisite for machine learning. As shown in the end of the heatmap generation flow on the left side of Figure 3, the parsed information from raw simulation data is stored in a comma-separated value CSV files. These CSV files serve as the input data for optimization problems and ML models proposed in this article as a methodology to reduce the pre-regression and coverage closure turnaround time, TAT. For ML, machine learning, to effectively use this data, raw data and undergoes data processing, which includes the feature extraction and alignment. Further ML approaches are suggested to enhance SDC verification. Three key features are extracted from the heatmap transformation. First, the number of asynchronous paths covered by the separate test. 2. The number of unique paths covered by separate test. 3. The number of paths that can be waived, such as count register paths. A sample of data set after pre-processing is a feature shown in 5. The Figure 5 is example dataset after feature extraction. So the data generated through the heatmap visualization can serve as an input for machine learning and optimization algorithms, and so helping to reduce the regression runtime. So since the heatmap is structured based on paths of the specified in the SDC, any uncovered field of the heatmap indicates the specification sources to destination paths that requires additional test scenarios. This highlighted the necessity for the dedicated test vectors to fully cover SDC constraint and supplemented the functional regression suite. To address uncovered path, we can add the directed test and modify the constraint in existing test to create new vectors to meet the required coverage. Moreover, the heatmap visualization is a value for a waiver decision when a paths specified in the SDC do not align with the design due to the version mismatches, or present that code. By providing a consolidated view of the test result based on the SDC information, the heatmap is identified the paths that may be waived from testing. Specifically, the test mapping for each path large follow extraction of feature dataset can be used for optimization and machine learning algorithms. So this feature datasets include key details such as the coverage scope of individual tests, simulation duration, unique path coverage, and extent to skippable regions within each test. So this information allows us to focus on relevant tests, minimize redundancy, and optimize the regression testing process, accelerating verification while ensuring the thorough coverage. B. Optimization, regression testing, and coverage closure with machine learning techniques. The SS coverage closure involved identified verification gaps, so they introduced new scenarios to address these gaps and iterating through the regression test to verify the changes. In previous section, the heatmap focuses on detecting and test suit. So the test based on a coverage result. Test priorities are set and the redundant tests are removed. With machine learning, the test suite is optimized, reducing regression time and accelerating coverage closure. The overall coverage closure flow is shown in Figure 6. SDC coverage, Figure 6 is coverage closure flow with optimizing test suite finding. This approach consists of two main components in Python, solving the optimization problems using the PuLP library and training a random forest classifier with scikit-learn. The following numbered sections outline each component and the regional follow using the PuLP and the random forest in this context. Role in the regional follow PuLP and the random forest. The PuLP library is used to formulate and solve a linear optimization problem, and thus the PuLP plays a crucial role in optimization test suite. By selecting a minimal number of the tests can be comprehensively covered the required paths while minimizing the redundancy. The library flexibility and ease of use in handling binary and integer values making it well suited for modeling test selection as a binary decision, 1 if selected, 0 otherwise. By defining an objective function that minimizes the number of selected tests while covering all paths, PuLP effectively prioritizes the high-impact tests and excludes the redundant ones, thereby optimizing regression test suite. So, the random forest classifier predicts the importance of the newly added tests and determines whether they should be included in the optimized suite. Random forest was chosen over other machine language algorithms due to its robustness, high interpretability, and natural ability to handle features importance. As an ensemble method that builds multiple decision trees and aggregates their result, random forest effectively manages diverse feature sets such as test execution, time and coverage contribution, and skip ratio, and without overfitting. With fewer hyperparameters than many other algorithms, random forest is also easier to tune for consistent performance in test suite optimization. 2. Objective functions and constraint in optimization. The goal of the optimization is to minimize the number of selected tests while covering all synchronized paths. These basic objective functions can be written in formula, where xi represents the binary value of each test, 1 if the test is chosen and 0 otherwise, with n as the total number of the tests, minimize something, minimize the summation of I to n and xi. In addition, each test unique paths, skippable paths, and the simulation time are weighted, yielding the final objective functions in Formula 2, where wi denotes the weight of each test, minimize the summation of the I to N is WI and XI. This paper considers only explicit constraints such as binary and path coverage constraint while excluding implicit constraint. The binary constraint defined in Formula 3 restricts each test xi to possible values 1 or 0. Xi is a subset of 0 and 1, or I is 1, 2, 3, and n. The coverage constraint shown in Formula 4 requires each path to be covered by at least one test, where represented all paths to cover, and Si is a subset of the paths covered by test I. Summation I, J, a subset of the Si, and Xi is equal to greater than 1, and all J is a subset of A. To optimize the solution, to find an optimized solution that minimizes the sum, the objective function and constraint can be implemented using PuLP library in Python. Table 1 provides an example of the pseudocode using PuLP. This code minimizes the number of selection tests while ensuring that all required paths are covered as per Formula 1. Table 1. Python code example 4 using PuLP open library. 3 is machine learning classifier and feature extraction. To improve the efficiency of the coverage closure, we applied random forest-based machine learning classification approach to reduce the number of regression executions. So the random forest is an ensemble method that trains multiple decision trees randomly to achieve a result in both the regression and classification tasks. This method is well suited for our optimization needs, as random forest is capable of handling various features with minimal tuning and can provide insight into feature importance, which is valuable in understanding the contribution of each test. For classifier training, we conducted supervised learning using a test set including features from prior data preprocessing as illustrated in figure table 2. So the result from selecting the optimized regression should serve as ground truth, and during the functional verification we predict whether new test scenarios can be added to the optimized regression suite based on a predict_proba values. If the value exceeds 0.5, we re-executed the optimization process and updated the regression suite. Table 2. Snippet of the Python code for ML training. By applying this method, we'll reduce the number of regression executions, thereby decreasing the TAT required for the coverage closure. The combination of PuLP for optimization and random forest and classification enables more than sufficiency and streamlined approach to regression test suite management, ensuring timely coverage closure and minimizing redundancy. Chapter 4 is the experimental result and achievement. This section presents the experimental result and outcome of applying the proposed SDC-aware verification methodology to a CPU block within the SoC design targeted high-performance computing (HPC) applications. The design includes the preferred such as GPIO, UART, I2, I2C, and SPI, QSIP, and a timer, along with the ARM Cortex-M3 and ARM Cortex-A55. It's called core processors. The core operating frequency is 1.5 GHz, and the design comprises approximately 10 billion gates fabricated in a 4nm process node. The SDC for the GPU block consists of the 1069 constraints, including the timing exceptions such as multi-cycle paths and port paths, which are the primary focus of this paper. These exceptions are defined using the 37 specific command, for example, set_multicycle_ the paths and set_force paths that affect a total of 82,554 paths in the design. Addition to a timing exception, the SDC also includes other constraint categories such as clock frequencies and constant values and I/O delays and clock groups. To validate the design, 554 tests test scenarios were implemented for the functional regression testing at the CPU block level. The goal of the verification process was to detect to design errors and achieve the complete SDC coverage closure by utilization of optimized regression suite and applying the machine learning techniques. We focused on minimizing regression test time while ensuring the full coverage of the critical paths. The key finding from the verification effort, including the identification of specific design errors and steps taken to achieve this closure. These results demonstrate the effectiveness of the closure methodology, improving the verification efficiency and accuracy of the SoC design, ultimately contributing to faster time to market and more reliable product outcomes. Identify the key SDC errors early through the X propagation in RTL verification. So the SDC-aware simulation logs and coverage tools typically provide an summarized numerical information such as the source and destination point, which limits the detailed debugging across the verification paths. This limited information makes it challenging to identify critical issues at the RTL simulation stage. By activating the X propagation during the RTL level verification, however, we can detect the two types of SDC errors that frequently overlooked before setting up the GLS environment. Both types of errors can lead to repeated mistakes potentially impacting SoC functionality and development timelines. Timing exception, constraint defined at incorrect points. Timing exception, constraint based on misunderstood clock relationships. Figure 7 illustrated of the example of detecting the first type of error. This error identified during the failed test message debugging with the X propagation activated. It typically occurs when a timing exception constraints are incorrectly defined due to the misunderstanding of clock relationship. Such errors can significantly impact the SoC functionality and require either an SDC or design change, followed by a full regression relearn after the fix. To improve the verification efficiency, this error is given a priority over others, allowing high-impact issues to be addressed early in the design. The second type of the error is depicted in Figure 8. This issue is identified during the cleaning and process or path test. It often arises from the misunderstanding as defining timing exception for asynchronous paths. While it does not immediately affect SoC functionality, it can be waived if deemed safe during the architectural review, as this helps reduce the verification workload and allows engineers to focus on more critical areas, streamlining the overall verification process. Figure 7 is detecting timing exception errors in a failed test with the X propagation. Figure 8 is identifying the waiving the asynchronous paths errors in past tests. The B. Efficiency gains in SDC verification through the optimization test suite and machine learning. The proposed heatmap visualization and machine learning based optimization were initially applied to a time verification of a specific IP within the SoC, demonstrating a measurable efficiency gain. Based on these results, we are currently expanding this approach to a SDC block level and examining the potential for a broader application across the SoC. Compared to the target CPU block design described earlier, the timing exception paths extracted for the specific IP were limited to 387. Through the SDC, the coverage closure for the specific IP instance, the optimization algorithm effectively reduced the regression test suite from 78 total test vectors to 19. Achieving the 100% coverage of timing exceptions paths defined in SDC, this optimization suite ensured comprehensive verification of the critical timing constraint for the IP instance while streamlining the test set. Contributing to overall the required efficiency, the result including a comparison of regression, suit size, and TAT between the proposed approach and existing method are summarized in Table 3. Using the optimization test suite to also reduce the regression runtime from 24 hours to 10 hours, achieving the approximately 63% reduction in verification time. This gain in efficiency translated to faster iterative cycles and reduced the engineering efforts to verification process, enabling engineers to allocate more time to other critical areas of the design validation. Table 3 is a summary of the regression TAT reduction achievement. In comparison to traditional GLS-based SDC sign-off, the approach was limited to a single test vector covering just one path with a minimal coverage score of 0.3%. By applying the proposed method to maximize SDC constraint verification, GLS coverage improved significantly. A single optimization vector verified 2 or 3 times the paths, covering the approximately 60% of the SDC-defined paths. This research demonstrates that an optimized suit enables a more comprehensive validation of timing constraint, particularly at SS block level, while the complex clock relationship and asynchronous paths require a lot of verification. Chapter 5 is the conclusion and future work. This study demonstrated that combining the heatmap visualization with the machine learning-based optimization enhances SDC verification by improving the coverage and reducing runtime. So the optimized approach streamlined the regression suite, achieving the comprehensive time verification of the critical paths while significantly reducing the verification time. The proposed methodology has been evaluated with a limited subset of the IPS of subsystem level. When applied to the block level or chip level, several challenges may arise, such as generating the heat map with thousands of rows and columns and determining the effectiveness of coverage closure based on these heat maps. Moreover, implementing this methodology at the chip level requires a comprehensive understanding of the system to define complex verification scenarios, and the development process where SDC verification must be stabilized in at a freeze point and replacing the current structural CDC and RDC verification or subjective designer reviews of the functional regression for functional verification and metric-based coverage closure provide an opportunity to ensure the objective reliability. This approach offers a significant advantage in improving the verification quality and mitigating risks to development schedules. So currently this methodology is applying to the block level, specifically the for LPDDR5 S controller N5, where the coverage closure is being performed for an SDC that requires verification of 64,202 paths derived from 318 constraints. In this section, this methodology has demonstrated a reduction in TAT turnaround time. Now, building on these findings, in future work we will extend this methodology to full full system SoC validation, further leveraging the machine learning to create a highly optimized and resource-efficient verification suite. Additionally, we will explore the AI-based predictive algorithms to dynamically define the test suite as the design complexity grows, ultimately supporting a fully automated SDC verification process. This extension will enhance the verification scalability and reliability, contributing to reduced development cycles and a faster time to market. Okay, today I read this paper, the enhancing SDC verification in SoCs, heatmap visualization, and machine learning approaches for optimal coverage closure from DVCON2025. Thank you for your time. See you next time.